Okay, so this is a problem that you might see in a lot of textbooks. It's something very similar to this. So they'll give you an arrangement of electric charges. In this case, I have three: a negative zero point 0.8 microcoulomb charge, a positive 1 microcoulomb charge, and a zero point 0.6 microcoulomb charge. These two are positive, and they form a right triangle. And they give these two distances. And the questions, I'm going to do this, the question answering what is the force on this charge right here. So let's start with the definition of the electric force. So if I have two charges, the electric force between them is going to be equal to this expression. 1 over 4 pi epsilon naught, that's just a constant. The product of the two charges divided by the distance between those two charges squared. And then you have to include this r hat here. So let's just, as an example, here's two positive charges. This vector would be r. But if I want to square that distance, then I can't square a vector. So you actually have to find the magnitude. So if I take that away, that whole thing is a scalar quantity. And I can't get a vector quantity unless I multiply by a vector. So that's where this r hat comes into play, where r hat is the vector r divided by the magnitude of the vector r. So this is a unit vector because it has it can describe directions. That's why. It has no units. It has a magnitude of 1, but this is how you'd find that. Okay. Oh, and this 1 over 4 pi epsilon naught is just a constant of 9 times 10 to the 9th newtons meters squared per coulomb squared. Some people just write that as K, and that's fine too. Okay. So let's do the thing first is to, in order to find, I want to find this force between these two. It's going to push down this way. And we'll call that F3 on 2. And then I need to find the force between these two, which is going to actually be this way because that's a negative charge. And that's going to be F1 on 3. Then the total force would just be adding these two together. But they're vectors, so I need to add them as vectors. Okay, and that's why it's important to write the force expression this way, because we're dealing with vectors. It's going to be much easier to do that. Let me start off with the positions of all these charges. So let's say this. R1 is equal to the vector 0, 0, 0. It's at the origin. And I want these all in meters. R2 right here is going to be the vector. So actually, in this case, they gave you this distance and they gave you this distance, but they didn't tell you this. Okay. So that means, but it's a right triangle, so I can say that's my hypotenuse. That's one side. I can use the Pythagorean theorem to find this, and I actually get something like 0.053. So this is going to be 0.053, 0, 0, and then R3 is going to be equal to 0, 0.606, 0. So let's start finding this force right here since it's the hardest. So the first thing I need to do is find this vector r, and let's actually call that r3, 2, because it goes from 3 to 2. So r3, 2 is going to be the position 2, r2, minus the initial position, r3. Okay, so that's not too bad, because here I have the vector r2 is going to be 0, 0.53 minus 0. So it's going to be 0.053. And then I have 0 minus 0.06. So negative 0.06 and then 0 minus 0. So remember, when I add or subtract vectors, I add or subtract their components. And that's what's nice about writing this in component form, because it's very easy to add and find vectors. Okay, now I'm going to need to find the magnitude. So R32 magnitude, I'll write it like this, is just going to be this squared plus that squared, square rooted, plus 0 squared. So it's going to be the square root of 0.053 squared plus negative 0.06 squared plus 0 squared. Okay, and I forgot to write down that answer, but you calculate that, put that in your calculator, and we'll check some things in a little bit. The next thing I need to do is find r hat. So r hat is going to be this value this vector divided by that value. So when I divide a vector by a scalar, because this is just a scalar number, I have to divide each component by that. So it's going to be 0.053 divided by this stuff, and then negative 0.06 divided by that stuff. And I get the following. I get 0.66. I'll round some so you won't get things perfectly. Negative 0.75. 0, and there are no units. And you can always go and check. I could take this, I could find the magnitude of this, and I should get a magnitude of 1. Okay, now we're ready. We're ready to find F32. It's going to be equal to K. Let's write it out. Let's write it out the whole way. 9 times 10 to the 9th. I'll leave off the units. Q1, Q2, which is 1 times 10 to the negative 6. Remember, microcoulombs means 10 to the negative 6. This one is 0.6 times 10 to the negative 6. And then r hat is this vector. And then I have to divide by the magnitude of this squared, which I forgot to write down. So I'm just going to write R32 squared. You can put that in your calculator. And when I'm done with that, I get the following. I've already calculated this. One of the things you should do is to practice with your calculator, because we have scientific notation, we have squares, we have square roots, we have all these things, and it's easy to make a mistake with your order of operations. So it's important to practice. So practice and put these numbers in and see if you get the same thing. And I get this: 0.558 negative 0.6330 newtons. Let's just double check. Does that make sense? Let's put that right here. Because it is going down and to the right, and this is to the right and down, so that's good. Okay, so we're going to need that force in the next case. So now we're going to find this force, the force between, this force, which is a lot easier. Okay, because it's all in the x direction. We're still going to do it the same way though. So the first thing I'm going to do is to find R12. That's going to be R1, which is, R2, which is 0.05300 minus R1, which isn't at the origin, so it's 0, 0, 0. So there you go. It's just this. Next thing I'm going to do is find the magnitude, and I can do this one. R12 magnitude. It's going to be this squared plus 0 square rooted, so you get 0.053 meters. Now I need to find R12 hat. It's just going to be this divided by that. So if I take 0.53 divided by 0.53, I get 1. If I take 0 divided by that, I get 0. If I take 0 divided by that, I get 0. So now I can say F12, let's put in all the numbers, 9 times 10 to the 9th. Q2 is negative 0.8 times 10 to the negative 6th. 1 times 10 to the negative 6th. Now my unit vector, 1, 0, 0. All of that over 0.053 squared. And I get negative 2.57, 0, 0 newtons. And let's see if that makes sense. So it's in the negative x direction. That does make sense because this is a negative charge and that's a positive, so they'll be attracting. That's going to pull this one in the negative x direction, and that's what I got. Okay. So now I just need to add these two forces right here. So I add these two, I add the x components, I add the y components of 0. Why did I put negative 0? That's weird. No, it's 0.0. That's not negative. That's a comma. That's a comma. That's a decimal point. Okay. So if I add these two, I get the total force. I get this plus this. I get negative 2.01. I'm rounding a little bit. If I add negative 0.06 and 0, I get negative 0.6 3, 3, and then 0. And that's my force. And that's a vector force. Now, some textbooks may say, oh, that's not good. You need the magnitude and direction. That is the direction. That is the vector. Okay. If you want to find the magnitude of that, that's fine. If you want to find the angle for that, that's fine. I think that's just pointlessly silly. But you know me. I'm just have an opinion about everything. So, okay, there you go. If you can find the force on this one, you could find this force. It's much easier because everything's in either the x or the y direction. All right.